Now, for most of the trusses we're going to see, whether they're roof trusses or bridge trusses, they're often loaded in the same way. Roof trusses have a load on the top, acting downward. Usually all the loadings are weights. Bridge trusses usually have a load along the bottom at the bridge deck, so to speak, where you're going to have vehicles or walking bridges, etc. Again, acting downward. They're mostly about supporting weights. You can usually guess that the top of the bridge is going to be in compression because it's trying to essentially collapse downward. As you push down on it, the top is trying to get shorter, so the bridge is going to be in compression. So the top members and the two outer members tend to be in compression. On the other hand, the bottom of the bridge is trying to stretch, right? You're trying to elongate that bridge, so the bottom member tends to be in tension. Now, uh, obviously, they're not always going to be exactly the same, and the shape of the bridge is going to affect them. In fact, if you take a look in your textbook on page 106, Table A, which is example 6.1, you can see an example of different types of roof trusses. And the flatter the roof truss, in terms of the angle, the lower the roof truss is, the more tension you're going to have on it, right? So flat trusses have to be stronger than taller trusses. Another issue is the various different types of building elements. The fact is, trusses are generally set up like this, but other buildings you're going to see use a variety of different systems. For example, the component that joins two roof rafters together is often called a collar tie. That's going to be up in the roof rafters. Or if there's no collar tie, you're going to potentially have that joined below right at the ceiling. Those are known as the ceiling joists. In fact, as collar ties, ceiling joists are going to be in tension. They're going to prevent the roof from essentially collapsing. All right. Some buildings you'll actually see cables in there. Right. These are all going to be tension members. Now, if you have very large buildings, these types of members would not be enough. So a common solution to that is to put heavy weights at each end, known as buttresses. They've been doing these for centuries. In fact, it's the way they were able to solve large cathedrals back in the Gothic period, where we used what we refer to as flying buttresses. Some nice examples of these in your textbook on page 107 in figures 610 and 611, which I recommend you take a look. By the way, between the top and bottom are various connecting members. These are not as easy to guess because they could be either in tension or compression, and it all depends on how the truss is put together, how it's organized or laid out, and how the forces are applied. By the way, these are general rules, and most of the trusses you're going to see will follow these, but it's not always the case. And the fact is, if a truss supports something other than weights or in a different location, then your potential for different types of forces are going to come up. Now, I recommend you now pause the presentation and take a look through the examples starting on page 105 in your book and in the course base. We're going to go through a number of examples associated with setting up trusses and creating free body diagrams, etc. The second method we're going to look at is our method of sections. And in this case, what we're going to do is we're going to cut the member or cut the truss up, right? And we're going to cut them through the truss members, right? It's not going to be at the joints. We're going to actually slice the truss members. And when you now remove those truss members, you're going to have to replace them with forces. And then, of course, we're going to first do a free body diagram and then analyze those sections. All right. In the sections itself, the forces from the cut members act like external forces. They act like something is pushing or pulling on it. If the member was going to be in tension, it would be pulling on the part. If the member was going to be in compression, it's going to push on the part. Now, fact is, these sections are two-dimensional. So the forces are not necessarily concurrent. They sort of act all over it. And in general, they're going to be non-concurrent systems. In that case, unlike method of joints, we actually have three equations to work with. They can be most often sum of force in the x, y, and moments, or moments. But the key thing about this is they allow you to solve for up to three unknown member forces. Right, so you can solve for three unknowns with three equations using the method of sections. Why would you use the method of sections, you may ask? Well, the fact is, if you are only trying to find the force in a specific member, you can make sure you section it at that specific member and do a single analysis. So whenever you're looking for only specific forces, then the method of sections may be more efficient. The fact is, it's a slightly more challenging method, but you can oftentimes go directly to the part you want to analyze. And while the method of joints is simpler, there generally is more steps involved. Now, as I said with method of joints, the first step is pretty much always going to be the same in the problems in this unit. We're going to take a look at the structure as a single rigid body, use our equilibrium conditions, force of the x for some moments, some force of the y, etc., equal to 0, to determine as much information as we can, usually solving for the reactions. We then divide up the sections, and we essentially repeat that same kind of analysis for each of the sections. Again, we can solve for three unknowns because we have forces in the x, forces in the y, and moments. But unfortunately, we don't really have triangulation. Triangulation only really works with concurrent forces or concurrent force systems. And in this case, we have non-concurrent force systems, so triangulation is really not an effective tool. So we really need to stick with summation for method of sections. In terms of cutting up the truss or structure into sections, a couple things you got to keep in mind. One, of course, you want to cut it in a efficient and easy place. So you want to cut it where you know a lot about, say, the dimensions or about applied forces. You certainly want to cut through the trusses, or I should say the members that you want to know about. But keep in mind, you also can only have a maximum of three unknowns. So you can only be cutting through three members. You can definitely do two members, but three is the maximum. Now, while you cannot solve for more than three unknowns in any one section, you can use the information from one section that you solve for as known forces in the next one. So much like joints, you can work your way through a part where you use the information from your first analysis in your subsequent analysis down the road. Now, as you saw from our drawing of trusses, they are pretty repetitive in terms of the nature. They usually have the same component over and over again. In fact, that's one of the reasons why trusses are used, because it's cost effective to make a single component and use it over and over again. So we're going to see that a lot in our trusses. And as a result of the fact that the shapes of trusses tend to be repetitive, then the analysis is going to be somewhat repetitive in that the angles will tend to be the same. Think about, for example, a Warren truss. Everything is going to be at 60-degree angles to each other. So the analysis is going to be similar in nature when we have similar shaped sections. Lastly, much like method of joints, this is self-checking as well. Whatever is essentially the last component that you've cut off that's left, you can always use that to solve, because at this point you have known all of the forces that are involved, and that one, just like joints, should also be in equilibrium, so you can check using that sort of last part. So let's take a look at this type of truss right here. This is not really a Warren truss. It's kind of a general truss shape here, because obviously we don't have 60-degree angles. We're not really given any dimensions, so we'll just think of it as a general truss. If we take a look, our first step in our analysis allowed us to solve for a sub x, a sub y, and f sub y. We now know that information. Let's say we want to find the forces in BD, in BE, and in CE, well, then we're going to run a section line right through. We're going to virtually cut this. Obviously, we're not physically cutting it. We're just doing it in our analysis. And wherever there was a cut member, we're going to replace it with a force. Take a look over here. We have section ABC. Where we had member BD, we replace it with force BD. Where we had member BE, we replace it with force BE. And F and CE, we replace it with force CE. All of these forces are aligned with the members, because keep in mind, all of the members are two force members. All right, so if BD was a horizontal member, then FBD is a horizontal force. FCE, horizontal force. CE, horizontal member. Whatever angle BC acts at, I should say BE acts at, FBE is going to act at that same one. Much like method of joints, we're going to assume that the forces are all in tension, right? So we see FBD pulling on point B, pulling on point D, FBE pulling on point B, pulling up on point BE. Does that mean all the forces are in tension? Well, the fact is, we don't know at this point. What do you think will happen if the members are actually in compression? Well, you probably guessed that's just going to give you a negative value for the force you solve for. Right? So much like method of joints, if you get a negative value, you didn't do anything wrong. It just means that that member is in compression, and rather than tension. Positive value, of course, it's in tension, and use a negative sign and label it as compression. Now, a couple of general notes about trusses and our analysis techniques. Fact is, you don't have to stick with one method or the other. You may find that method of joints is effective for one part of the truss, while method of sections is more effective for another part. You can definitely mix the two together, and as an engineer analyzing these, your method is up to you, and you can definitely use multiple methods in the same given problem. Another efficiency to keep in mind is taking advantage of symmetry. As we said earlier, a lot of trusses are somewhat repetitive, and in fact, many of them are very symmetric. Most roof trusses and bridge trusses are symmetric in that they are supporting the same load on either side, so they're built the same way on either side. Now, it's important that they be absolutely symmetric or completely symmetric. Even if one member is off, they are no longer symmetric and you can't take advantage of it. But if you have a structure that is completely symmetric, meaning all the components are the same, are mirrored left and right, it could also be mirrored top and bottom, but it usually is left and right, and this is another part, is exactly symmetrically loaded, so all the loads that are on the right are the same as the loads that are on the left, then you can determine that the forces in symmetric members are equal. Right? So if, for example, we had point A and point E were the two ends of a truss, essentially all the forces acting on point A would be exactly the same as all the forces acting on point E, and you could set them to be equal. Now I'll be doing an example on these, and there's a couple of videos on the course base I recommend you take a look at if you're at all confused about this. And why would you want to go about doing this? Well, the fact is, it's going to reduce your analysis steps significantly because you only really have to solve for half the truss. If it's exactly symmetric, when you solve for the left half, you can use that information to solve for the right half, and which will reduce your analysis steps by about 50%. Now, I recommend you pause looking at these lectures and take a look at the examples and textbook problems in your textbook. They start on page 114. There are also a number of examples in the course base that are worked out that also could be valuable, and take a look at those. As always, if you have questions on any of them, don't hesitate to get in touch with me, and I'll be happy to go over any of these problems with you in more detail.